So let's look at how to calculate the parameters of the regression line. So the formulas here are a little bit nasty, so you'll find them in your book, but this is section 12.2. The regression line has the following form. Y is equal to B0 hat plus B1 hat times X, or also alternate notation that's used in the textbook is B0 plus B1 X. And we want to come up with formulas for B0, the intercept, and B1, the slope of the regression line. So again, you'll find these formulas in the textbook, but the formula for the slope is given by B1 first, or beta 1 hat. It's the sum of the xi minus the mean of the x values multiplied by yi minus the mean of the y, so the sum of those cross products, divided by the sum of the squares of the xi values minus the mean values. Okay. We've used notation like this in the past, way back in chapter 1. The numerator we denoted as capital S xy, and the denominator is S of xx, the sum of the squares of x. Again, calculating these is a little bit messy. I'll show you computation formulas in just a bit and show you alternate ways of getting those. The formula for the intercept, B0, is a little simpler, or beta 0 hat. It's just the sum of the y minus beta 1 hat, which we now have, times the sum of the xi, all divided by n. The sum of the yi divided by n is just the mean y value, and then the sum of the x divided by n is just the mean x value. So to get B0, it's the mean y value minus B1 times the mean x value. Actually, instead of computing these summations using these formulas, there are simpler computation formulas that are easier to use when you lay out the data in a table. And so an alternate formula for calculating SXY. So here to calculate it this way, you'd have to go through and first calculate the mean value, and then go back and subtract xi from xi, the mean x value, and do the same for yi, and then take that cross product. Again, it doesn't take too much longer than this method, but it usually does take a little bit longer. And these formulas are a little bit easier to lay out in table formula. So an alternate formula for computing SXY is it's just the sum of the xi, yi product pairs minus the sum of the xi times the sum of the yi. Let me go back there. Times the sum of the yi, all divided by n. And for SXX, it's the sum of the xi squared minus the sum of the xi, then we square that sum divided by n. So I'll show you an easy way to do this. Going back to that data set we had in a previous video, we had the xi and the yi values, and we had, I'm just laying them out vertically now, we had 1.2 and 22, 2.0 and 41, 2.9 and 58, and 4.1 and 82. Okay, so from this we can compute the sum of the xi just by adding up these values, and that's 10.2. And similarly, the sum of the yi is 203. We'll have another column here for xi squared, where we square each of the values here. So 1.2 squared is 1.44, 2 squared is 4, 2.9 squared is 8.41, and 16.81 is 4.1 squared. And then the SXX term involves the sum of the xi squared. So now that we've got all the xi, we can sum them together, and that turns out to be 30.66. And then the other term that we need is xi, yi, and taking the products of each of the terms. 1.2 times 22 is 26.4. Product of 2 and 41 is 82. 58 times 2.9 is 168.2. And finally, 4.1 times 82 is 336.2. And then so now we can add up all these terms and get the sum of the product terms is 612.8. So now with this table, we've got all the terms that we need to calculate both SXY. So it is equal to the sum of the XI, YI terms, so it's the 612.8 minus the sum of the X, the 10.2, times the sum of the Y, 203, divided by the number of observations, or 4. And so that turns out to be 95.15. And similarly, SXX is the sum of the XI squared terms, 30.66, minus the sum of the XI squared divided by 4, and this turns out to be 4.65. And then so finally we can now compute B1, or beta 1 hat, is SXY divided by SXX, and that turns out to be 20.46. So this is actually the slope of our regression line, and B0, or beta 0 hat, is y bar minus beta 1 hat x bar, or y bar is going to be the sum of the y, 203, divided by the number of y values divided by 4, and similarly, and then our beta 1 value is 20.46 times the sum of our x is 10.2, and then divide by 4. And so the B0 value turns out to be minus 1.429. So it took a few minutes to compute the intercept and slope of our regression line. And here it was, even for a fairly small data set. You can imagine that you don't want to do these computations by hand if you're dealing with large data sets. A lot of calculators will do this for you. You just enter the X and Y data, and it will automatically compute the intercept and the slope of the regression line. You can also use Octave to do this relatively easily. So in Octave, SXY is equal to the covariance function, covariance of x, y, and we have to pass the third argument 1 here. Without, if you leave this off, it computes the sum of the products and divides by n minus 1. But if you use the 1 argument, it actually divides the covariance is the sum of the cross products divided by n. So we need to multiply by n to get the sum of the cross product terms. And then similarly, SXX is the covariance of x and x times n. Of course, for n, what you typically use in octave is the length of your x vector or your y vector. They are the same length. And then so in octave we can compute the slope SXY divided by SXX. And if you'll notice here, when we take this ratio, the multiplication by n will cancel. So it's simply the covariance of xy1 divided by the covariance of x comma x1. You can optionally actually omit the 1 here, because if we omit the 1, the xy terms is the sum of the xy divided by n minus 1. But then similarly here for the covariance, it would be the sum of the x squared terms divided by n minus 1, and that term would cancel out. And then to get B0, it's the mean of y minus, now that we have B1, times the mean of our x values. So let me show you an example. So this is example 12.4 from the textbook on page 479, where I'm going to use octave. So let me bring it. So I forget what the data set actually is here. Here the data consists of, it looks like 14 observations of x and y data, and then here's my M file to actually read the data in. Let me increase the font size here a little bit. So again, I read in the data using DLM read. Data is going to consist of actually 14 rows of 2 columns. My x data is in the first column and the y data is in the second column. So here's how I compute B1, the slope term. Here's how I compute B0. And what I'm going to do here is do a scatter plot and then hold that plot. That's what the hold on line does, and then plot my regression line. So I've got my formula for my regression line. It's B0, the intercept, plus the slope times, and I generate a vector of just x values here that don't correspond to my data values, but are just x values that I use to draw my line. And I generate that vector. It has 100 points between the maximum data value and my minimum x data value. And then I generate a corresponding y vector. And then so when we plot that, you get this. So the circles represent our data point pairs in our scatter plot. And then here's the regression line. In this particular case, if you look in the command window, the y-intercept is 75.2, and the slope of the line, it is a decreasing line, so it has a negative slope of 0.209. So again, let me pull back up the graph. Again, if you can imagine this graph being extended onto 0, looks like the y-intercept would correspond roughly to 75, and we see it has that negative slope, and looks like there's a change of it goes from maybe 63 to 48, a change of 15 over about 70. So I'm guessing that gives me the 0.21 slope that I got from the calculations.